All right, guys, I hope you like designing antennas to Miles Davis, because that's what we're doing today. We're going to focus on the reflector antenna, and on a couple of other video segments that I'll make before Friday, we'll deal with the capacitor, with Cade's monopole antenna, and I think maybe that's all that I owe you guys. So let's get started. We're going to start and keep this super simple. I'm going to go to Automation tab, remember Show Hide ACT Extensions, and I'm going to choose HFSS Antenna Toolkit. And when that comes up, I'm going to go straight to Reflector, and I'm going to choose the parabolic reflector. I'm not going to make any changes to these defaults whatsoever. I'm just going to say Finish. So this should generate very quickly for you. And when we get a full model over here and our tree builds out, I'm going to go to simulation. I'm going to verify, I'm going to validate, make sure that I get a bunch of green check marks. Notice this is all running some stuff in the background right now. Depending on how many people are on the server right now, maybe yours is running a little bit slower, but this is going to fill out pretty soon, hopefully within another minute or so. And I'm just going to solve this project as is, so we'll have something to talk about. So I'm expecting you to do the same. I got something that's got the offset. It's larger in one dimension than it is in the other. That's all fine. We can change this later. I'm going to go to Simulation. I'm going to hit the Validation button, and I'm going to close that, and now I'm going to choose Analyze All. I expect this to take maybe a few minutes. I've got 8 cores. You can check yours if you're running this on the, well, of course you're running on the server. When you go to HPC options, don't forget you can verify by hitting the edit button and see how many cores you have. I recommend taking all of them. You'll battle each other out if you're running at the same time, but I wouldn't worry about that right now. If you guys want to negotiate, that's fine. But if you've got 24 cores available, go ahead and use them all so you get a solution as soon as you can. I'm going to pause while this is running for me. I'm going to kill this window. You can see I've made it to adaptive pass. If you've been following along exactly, hopefully you've also made it to at least adaptive pass 1 by now. I can't remember how many adaptive passes we need for this to solve all the way through. So I'm going to pause while this is continuing on. So about 20 minutes has gone off of my clock, and I assume maybe yours might still be going. One thing I wanted to point out was there are different solution processes happening in sequence. You can see right now in my progress bar, it talks about 4 frequencies. It basically solved 4 frequencies with 4 being solved in parallel. Yours might have different numbers, but one of the key points here is that once you make it to frequency sweep right here, that means that the adaptive pass is done. We can look at the antenna pattern and figure out the gain for the solution frequency. So solution frequency is different than this frequency sweep. It could be inclusive of, but not necessarily identical to. So I'm going to let this continue on, and if you see a FF3D gain total that has been generated and it's no longer shadowed out, that means that you've also made it through the adaptive pass as well, and you are probably in frequency sweep mode. If not, pause this video and wait till you get to that point, and then you would be able to follow along with what I'm about to do. So I'm going to scroll down to the radiation node here, and I'm going to right click on what's called ATK_3D, and when I do that, I'm going to compute antenna parameters. When I do that, it is giving me a number of different variables. Some of them, or I should say values, some of them we talked about in class, others we didn't. And I want to draw your attention straight. Let's go ahead and widen this a little bit so we can see everything. The main thing that I'm really looking for is this peak gain. So this is a value, it's a dimensionless value, it's the gain. It's identical to the thing that we talked about in class, measured in dBi. This happens to be a linear dimensionless object. So what that means is that 10 log needs to be applied to this number that you're looking at in the peak gain value table for this to be something you can use in the link budget that the mission team is coming up with. So If I were to just do this, I can pull out the calculator, and let me just to be perfectly clear, I'm going to type in this number. Whoops. Let me minimize that. And 2122. If I type in 2122 and I do log, it's assumed that it's a base 10 in this case. I get this value, 3.3, and of course I have to multiply that by 10. So this value that I'm getting is 33.3 to the first digit dBi. So one question is, does this meet the criteria for the gain of the vehicle that's either in orbit around Mars or the rover that's on the surface of Mars? And I think we found that this does. So that's good. We can just use this default value and verify that it's going to work with that gain equation. What we're going to do is switch now and start evaluating the ground station. So in order to do that, I'm going to make some changes to these variables in a different design. This is still solving. I'm going to let this continue on all the way, even if it takes another 20 or 30 minutes. That way I can always come back to this result. So if you're still solving, I recommend that you let it continue on until we're completely done, and then come back to the stage where I'm copying this design and I'm pasting it into the same project like we've done in class. And we'll start working on our Earth station, the JPL base station. So I no longer see progress bar moving. I no longer see messages popping up. I don't have any errors. If I expand this, I see normal completion. So that's great. I can keep track of my time. This was done at 12:43 for me, and it looks like it's started the discrete frequency sweep. These times don't appear to be heading up the way that I thought they should be, but that's okay. I'm going to save it. When I go to results, I can always go into the solution data and look at my profile, and I'd get a complete history here. This tells me that my elapsed time for the entire solution process was 32 minutes. I think you're going to see something similar, probably a little bit less if you use more cores. So before we copy this, I do want to talk quickly about why we were waiting so long. These anything that says gain up here in these results probably showed up as unshadowed a lot quicker than these things called return loss and input impedance. I'm not going to look at the impedance, but let's double click on return loss. And what this shows you is that when we saw a number of frequencies were being solved, in addition to our primary solution frequency of 10 gigahertz, HFSS went ahead and solved frequencies much lower and much higher. And that's because typically antennas are going to operate at frequencies that are, you've got multiple bands is what we call them. So transmit signals might be coming in at slightly different frequencies than receive signals, those sorts of things. And that's why we spent the extra time to wait for that. It has to do more work to be able to get those frequencies. So I'm not going to talk too much more about this thing called return loss. These values, I can tell you, look very good. The fact that it's less than negative 20 dB for a very broad coverage across multiple frequencies, that's a very good result. So it indicates that we probably have a good design. So that's all I'm going to say about that. I'm going to go back to this. I'll double click on this guy, and what I'm going to do is I'm going to right click, copy, and I'm going to right click on the project and say paste. And when I do that, you'll see my original parabolic ATK. It has the exact same name, but now it has a number 1. It's just a revision. These results don't exist. Whenever you cut and paste the design like that, the results are they're removed from. So we would have to set up. We would have to resolve if we were going for the exact same frequencies and settings, but we know we're going to make some changes. First thing I'm going to do is save. Remember where you keep your design. I know where mine is. I can always get back to this ATK1 project. But this is going to be a new solution with new settings. So let's see what happens here. I'm going to right click in this window, clear all these messages. so that I know I'm seeing current. I'm not going to get confused over old messages, things like that. So let's start by, I'm going to leave the feed location where it is. So let's just leave that to be 0. But I'm going to change the radius. Actually, yeah, I'm gonna make it slightly bigger. let's say 50 centimeters. And now let's go to the minor radius and make that 50 centimeters as well. And it's circular again. So far this makes sense. Look at my offset. I'm going to change my offset to be 0. And all that appeared to do was basically pivot the direction of the horn antenna, and it also seems that it changed the shape a little bit of my reflector antenna. So let's get an angle here of this. I can always use these buttons here to kind of get my view. One thing that I'm realizing is that well, I guess that we have to keep track of. Remember that we're designing with a radius here, and I think this came up in class. Make sure that you keep in mind that the radius is only half of the actual diameter. So if we're going to build from the 70 meters scope, I should say antenna, we have to know that that 70 meters applies to either the radius or the diameter. I believe we found out that that was the diameter. So for now, 100 centimeters is about 1 meter in size. So we made a little bit larger. We kept everything else the same. Before I solve this for another baseline design to make sure that our changed settings is going to give us a different result, I'm going to go into analysis and I'm going to disable the sweeps. Those were taking a really long time and we don't need them moving forward. So I'm going to right click and say disable that, and I'm going to disable the other sweep as well. 2 frequency sweeps. It's going to save a lot more time now. So I just want to go back into simulation and validate and make sense that I'm getting what I expect there. If I right click this design, I should say the setup, ATK solution, and analyze, I'm going to watch it go through the same process of the adaptive pass. But I don't expect to see anything on the frequency solve. So I'm going to let this go for a little bit, see if I can get this to give me a new solution, and I'll compare the results for just the measured gain, the way that I just showed you in the previous result. So I'm going to pause the video while this runs its course. Keep an eye on this. Make sure you get to probably adaptive pass 2 or 3. I'm hoping, even though we have a larger size, it's going to be slower. But since I turned the sweeps off, it should solve a lot faster. So I would think maybe less than 15 minutes for this solution is my hope. But let's see what happens. I'll come back when I make some progress on my side. Just a quick status check. I made it to adaptive pass 2. I've been going on for a few minutes now. I'm going to just go to results and solution data and go to convergence to see how things are looking. If I go to the plot here, still being on pass 2, I don't have enough information to plot for the convergence. So one important thing about looking at the quality of your solution is that we always need at least the second pass to be completed for us to actually make a measure of whether or not convergence is there. So I'll come back in a second. Hopefully yours is still solving along. If you have adaptive pass 3, you would probably see information in this plot. And we're trying to get to this 0.1 max magnitude delta, and that'll tell us that our result is accurate. So I'll pause and come back again when I have more to discuss. So another status update. I'm on adaptive pass number 3 now, and just in case I misspoke earlier, you can see this is starting to build out. Our convergence criteria is shown here in green. It says target magnitude delta S. That was set up in our initial solution setup over here. If you double click, you'll find 0.02 is in there as a default. So with this adaptive pass 3, the hope is that this number changes from, it looks like 0.01, this would be 0.02, 0.03. It's a little above 0.03 right now. Actually, you can see the current right here is 0.031. The hope is that when adaptive pass 3 is complete, we'll get another dot that's going to show up below the convergence criteria. If not, it'll do it again. And every time it does it, it's adding more and more mesh elements, and you can click through some of these tabs and verify that while that's going on. But this is just background. Again, you don't need to know all this in detail. I'm just trying to provide a little bit of context about why we're waiting for this solution and what the value is. So I'm going to pause again, hopefully come back at the end of pass 3 with a completed solution, and we'll take it from there. So as expected, we've actually made it. We can see here our previous result at the second pass, and then what's showing is the current result, which is 0.008, just below our threshold quite a bit. So when we get to the third pass, we actually met our convergence criteria, and that's exactly what it's telling us. It's telling us we have a converged solution. That means it's as accurate as we asked for it to be. So now I'm going to close this out, and I'm going to do a quick check on the value of the gain. So I'm going to go to radiation, right click on ATK 3D, compute antenna parameters, and let's see if we can pull this out. Looks like, well, here it is right here. So that appears to be a different number. So it actually appears to be a much larger number. So let's plug that into our calculator, 6861.2. So if I go to, I must have closed my calculator. I'll bring it back up. And I'll type in 6861. I'm going to do log, and I'm going to multiply it by 10. And now, this is a higher gain value, I believe. So 38.4 dBi, as opposed to, let me minimize this. So we can actually just remember that number, 6861. When I close this and I go pull that number from my previous solution, right click, compute antenna parameters, and sure enough, the peak gain there, that was our previous calculation. So we have tripled it on the linear scale, but of course in a decibel scale, it's not going to show up as a tripled number there. So just to be clear what I'm talking about, let's just remember this number of 38.4, and I'm going to recalculate here. And I'm just going to type in 2122. And if I go to log times 10, 33. So it's only gone up 5 dB. That might not seem like a lot, but in the linear scale, we have to keep in mind that doubling a value in the linear scale is going to be adding 3 dB to it, 3 decibels, which 10 times the log of that number is the definition of decibel. So that takes a little getting used to, maybe, but we've actually increased the gain quite a bit just by making the aperture, that's a term that we use for the size of the reflector, a little bit larger without agonizing much about the focal length. We kept everything else the same. So it's a really good start. This is telling us that we should be able to continue to tweak these design parameters and come up with something that's closer to that really large dBi value that we need, which I think was maybe somewhere maybe in the 50s or even the 60s of dBi for the land-based antenna. So I will save this. We've got a really good start, and we'll come back and do some further changes. As you probably guessed, I'm going to copy and paste this design into the same project, and we'll continue to make some changes. So before we make a copy of this and move on to the next iteration, I want to take a moment to look at one thing. I'm going to go to Solution Data again in the Results tab, and I'm going to go to Profile. And let's take a look at that elapsed time. So 21 minutes, almost 22 minutes is what it took for us to solve this antenna with those last changes in the settings, and we turned off the frequency sweeps. So keep that number in mind, about 22 minutes total time. And that's important because what we're about to do should make a big improvement on the speed of the solution. I'm going to copy ATK1 and I'm going to paste it. So now I should get parabolic ATK2. All I'm going to do right now, without explaining anything further, is make a change to the hybrid regions in the new design. So go into the new design tree, expand out hybrid regions. When you see hybrid reflector underneath the hybrid regions node, double click that. And I want you to change this to SBR plus region. I only introduced that idea in class without spending much time on that. I'm going to validate. It's telling me that there's an analysis setup. Okay, so this actually makes sense. With this type of solution, we need to set up what's called an observation domain. And I think I did this in class. I'm just going to double click ATK solution here. And in options, I should look at, actually it's in hybrid. It's in the hybrid tab. It's asking me to set up this field observation domain. We already have these set up underneath the radiation node. I'm going to choose ATK 3D. And that should be all I need to do. I'm going to say OK. And now let's see if we pass validations, and we do. I'm going to clear these messages so I don't confuse them with any new ones that pop up. And I'm going to, I can analyze all at this point. Everything is already solved. And I turned off all my additional sweeps. Or you can continue right-clicking the ATK solution and analyze that way. So we are probably going to see maybe a difference in some of the messages here. It's still going to do the adaptive pass, but the speed of the solution is going to be much faster. You'll find out here because of the two different solution techniques that are being used for this. So this is going to be going through probably a good bit quicker. I'm going to go ahead and pause this. Maybe actually while it's running, I'm going to go ahead and bring up results. And I'll go to solution data, and we're already on adaptive pass 3, so that's great because we can get a feel for the convergence. I go back to convergence here, and I'm going to go to plot, and I should see this starting to build up. 0.01, so we met our converged criteria pretty quickly. So this is going to wrap up in a second. Notice how it's in this shooting and bouncing ray phase, and just like that, our solution is actually complete. So no need to look at the profile. We know that whole thing was less than probably 2 minutes, maybe less than a minute. So that's great news. Let's go ahead and see if we can look at the gain of this. I guess my question for you is, before I go into the node, would you expect the gain to be any different than the last design, which was ATK1? So think about that as I right-click on this and I look at compute antenna parameters, and I see a peak gain. And I asked you if you would expect the difference there. And since I didn't change anything with the diameter of the antenna or the location, any of those at all, my thought is that I wouldn't expect there to be much of a difference. So how do we explain that the number is slightly different? If you remember the last value, just try to remember this 7071. We'll compare that to the previous solution. If I come into that design and if I right-click compute antenna parameters, it's pretty close. It's actually very close. So why is it different, I guess, is the thing I'm trying to get you to think about. And the reason it's different is because these are using different solvers. So when I asked you to change this hybrid reflector node in the newest design to an SBR plus region, it's actually using a more approximated technique than the previous technique. So if we're okay with maybe some of the reduction in accuracy with this new technique, because it's all in the interest of getting a very fast solution, then that's acceptable. So this technique applies quite well to large reflectors at high frequencies. So we're in pretty good shape with this. So this should encourage you a little bit for maybe what the next iteration is going to be, where we're going to look at maybe trying to get close to our actual JPL size reflector, and that's what I'm going to do in the very next. And as you guessed, I'm just going to copy and paste this parabolic ATK2, and maybe that'll be our final design, and we'll actually be able to hit that target. In the process of doing the copy and changing our design type, we lost the result of the radiation pattern. So return loss and input impedance is still present. That wasn't the one that we were really interested in. I'm going to show you how to create a new radiation plot or a gain plot. So I'm in the results tab and I can see far field report. As soon as I open that, I can choose what's called 3D polar, and I want the category of gain for now. Gain total is fine, and I want to present this in dB scale because we're looking for dBi. So with that, the only last thing I need to do is choose the geometry, and these are those references that you see down here. In this case, I've got this ATK 3D, and that's the one that it sees as the 3D sphere. So I'm going to choose new report, and now I get one called gain plot 1. So you ought to always be able to reproduce this. So I think you guys saw this in class today. This looks familiar. It's another way of picking out the maximum gain of the antenna. You can see I've got my color scale here, but it's also telling me that right here at 3.8 dB, actually that's times 10 to the first power, so it's actually 38.5 dB is the max gain that I can see here. And again, that's not resolved very well because our sphere wasn't resolved very well. That's fine. We're okay with this. So now you know how to generate a 3D gain plot. We can always refine it a little bit as needed. So I'm going to close this out. Actually, let me go in here. If I right click on, let me do this one last thing now that I think of it. If I right click on this and I choose show in modeler view, then when I select that means when I double click the top level node here, I can see it superimposed. So it gives you a nice feel for how the orientation is with respect to the actual physical thing that we're designing. So sometimes that can be very helpful. For now, I'm gonna come back and just turn that off. So now it just disappears. Okay, I'm gonna save this, and now we're gonna make some changes to our new baseline. So right now, I think the best model that we have is gonna be this parabolic ATK2. It's larger in size than the original. It's set up very similar to what the JPL ground station looks like. Now what I want to do is copy and paste this as a new iteration, and I'm going to make sure that this is highlighted. So whenever I see it bolded, I know that I'm operating on the one that I see, if that makes sense. So we're going to change these values and see if we can get them to match up a little closer with the JPL telescope. Or I keep saying telescope, I mean to say reflector. So the major radius, if it's 70 meters, that means a radius would be 35 meters. So in centimeters, that would be 3,500. So we'll make that change first. We get quite a difference here, and of course that's not going to work for us. So let's keep making the changes here. I'm going to go 3,500 on the minor radius, and now on the focal length. The focal length is defining the concavity of this parabola. 50 centimeters is very close. If I remember from class, one of the ones that you guys were considering was like a ratio of like maybe 5 to 8 or something like that. So I'm just going to make up a number. Let's say 2,000. That's kind of like a 4 to 7 ratio, I guess, if we're talking about diameter. And if we do that, this starts to look a lot more like what we would probably expect. If I zoom in here, I can see, yeah, that my diameter appears to be right. It's less than 80. So yeah, it looks like it's less than 70 meters. You can see, given the distance, the focal length of this guy, it's different than necessarily the location of the feed. But this might be a valid start for us. So we're going to see what we can do now. I'm going to save this design. There's nothing else that needs to be done at this stage. Everything should be set up. All I did was change a couple of parameters. Now I'm going to go to simulation. I'm going to make sure that that's the case. I pass validation, and then now I'm going to go ahead and hit the Analyze All button. And it's larger than the last design. It's probably going to take longer, but maybe not a whole lot longer by using this hybrid shooting and bouncing rays region. It's probably going to speed the solution still significantly, even if it is a little bit slower because of the size of the reflector. We'll let that go through its adaptive passes. I'm guessing just a few minutes here and we'll be done. So I was a little off on my time estimate. This thing is cranking away. We're at the end of adaptive pass 3. That's great. And you should see shooting and bouncing rays. There are good reasons for why this is probably going to take a lot longer than I thought. So I'm going to let it run its course. I'm not sure how long this is going to be. If you're in the middle of other things, I recommend staying on the server, let it solve, and just keep an eye on it. I can't tell how this progress bar is really going to correspond to actual time. So I'll check back as it makes a little bit more progress. One more quick time check. It's probably been near an hour and a half. I've been off doing other things. This solution is certainly chugging along, and it's going to make it, I believe. I don't think we're going to have any issues. So I'll check back in an hour and a half, 2.5 hours or so. I'm going to let this run. If you've made it this far, I recommend you launching this simulation and just letting it go overnight or something like that. We do believe it's going to get there. So this is all good. And keep in mind, if this is so slow using this hybrid technique with shooting and bouncing rays, it likely means that it would be completely impossible to get it with the other solver techniques for reasons that we can hopefully touch on maybe next week a little bit. So let's let this keep going. I'll try to check in, or I'll hopefully show you an actual solved result. All right, it's dark outside. I came back after several hours and we have a completed result. I'm going to look at the message manager and it tells me normal completion, so that is certainly good news. Let's go to the profile real quick. I just want to see maybe how long this took. 5 hours, 5.5 hours using the hybrid technique. So let's see if we got anything that makes sense. I'm going to go to, actually the far field report should already be generated here. So if I just double click on this guy, wow, we see quite a bit of gain here. So it looks like a peak gain of about 64 dBi. And again, that's, kind of an odd looking pattern, but that's got a lot to do with the way that we rendered it. In reality, that sharp spike is not as sharp as that. If we put more points on our observation sphere, we would actually see that. So let me give you an idea what I mean. If I go to radiation pattern and I double click on this guy, this is basically telling us the spacing of the points that are creating that sphere. So imagine if we were centered on the antenna and we went from 0 degrees to 180 degrees in 5 degree steps, and then in the other direction went negative 180 to 180 in 2 degree steps. If we basically made this a higher resolution, like maybe half degree steps, you wouldn't see that pointy structure right there. So either way, the solution is real. It makes sense. And it probably meets or gets pretty close to meeting the gain targets that Howard was looking up on the websites for JPL the other day. So this would be the gain of the transmit antenna, and we should be able to plug that into the freeze estimate from the mission team and see if this actually makes sense. So that was still a pretty long run time for a solution. It's very doable. If I have time, I'm going to look at different techniques when I evaluate the two antennas. I got a design from Howard, and I just got a design from Kivern that came in. And hopefully if I have time tomorrow, I will look at those and how to set those up in something that's a little bit faster, still using SBR+, after I get to Cade's antenna design. So I think that's it for now for this parabolic. I think you got a good idea of how to reproduce this. So hopefully you're able to do that with your own designs as well.